So the slide is called the example of subspaces. I chose two examples right now, and I'm going to show you like a general approach to such examples. First one is I call the S1. It's the collection of vectors from the R3. And remember, when we write, it's something I was trying to make very explicit for you on Thursday. If I write a symbol like this in a vector space context, in my head, I see not the symbol, I see the quadruple of objects. So here's my S1. So it's a collection of vectors with three components, x1, x2, x3, and the components are subject to the condition like so. This is a tutorial question 17. And the S2, it will be the collection of vectors, again from the R3, from the three-dimensional vector space, with the components x1, x2, x3 subject to the condition like so. This is a tutorial question 16. We have to answer, in fact, question 17 says prove that S1 is a subspace. Question 16 says prove that S2 is not a subspace. So first we're going to address the question 17. We're going to analyze this the subset S1. You see, I'm not calling it subspace yet because we haven't shown that yet. And I'm going to do it from the general perspective. I'm going to discuss the following lemma with you. Look at this. The lemma says this: if I consider this set a general set of the following structure, S, you see, sub R, as for reals, and here in brackets I have some vector A, and the set is defined like this. It's all n tuples. You see, I'm doing the general case, not specifically the three-dimensional one, but n-dimensional. All n tuples which are subject to the following condition. Look at this: x dot product with this fixed vector A is 0. I claim that this will be a subspace. Why do I do that? Well, if I have this more general result, so here A is just a fixed, A is a fixed n-dimensional vector. If I prove that the set of such structure is in fact vector space, then I can answer the question in relation to S1 by simply referring to this lemma, by simply saying that S1 is the set of this structure for the particularly chosen vector A, this vector A. If I choose in place of this vector A, 2, 3, negative 4, this condition will be exactly the condition of perpendicularity like this, dot product being 0. And if you will do the questions in the yellow book, you will see that the great deal of questions about the subspace, they all fit into the same scheme of something being of collection of vectors from Rn, and will be 2, 3, 4, 5, 6 of your choice, and all of them will be perpendicular to the given vector. Question 17, just one of these such questions. There will be lots of other questions which fits into the same scheme. That's why by addressing the lemma here in class, I will kill all of those birds with one single stone. In fact, I have two parts in my lemma. This one is part alpha. I can do a similar construction where I replace real numbers with complex numbers. So my lemma in fact has a part beta, which says if I do the construction like this, S subindex C for complex numbers with the vector B here, such that my Z it's a collection of all n tuples, that this time with complex components, such that they are perpendicular, and we know the dot product can be done also on complex vectors as well, perpendicular to this given vector B, such a collection is also a subspace. I'm not going to prove two parts. I mean, you can argue this part by analogy, as long as you know the argument for this part. But now you see why I use the subindex R here, to emphasize that these are the vector spaces over the field of scalars. Real numbers and these are the vector subspaces or vector spaces over the complex numbers. So given that if you believe for a second that the lemma is true, then the answer to question 17 will be a simple reference to such lemma, because my S1 presented in the question 17, it's simply a vector space of such structure. So from here we will conclude, given that the lemma is true, that S1 is a subspace. Let's just see why the lemma is true. Here's my proof of part alpha of my lemma. And we're going to argue, like I said, every time you argue the subspace, you will argue by the subspace theorem. That's the shortest way to argue. Questions like this? Well, it's the shortest direct argument. I mean, the argument which is here is just one-line argument. By the reference to this lemma, it's even shorter argument, but it's like an indirect argument. We use a reference to the existing result. I mean, it will be existing in a second when I finish my proof. So if I test that the set like this, if I want to test the set like this as a subspace, I have to follow the subspace theorem. There are 3 criteria there. Each of them has to be tested individually. Here's a test of the first criterion. The first criterion says 0 must be in this subset. Well, we just do a direct check. If I do a dot product between the 0 vector and my vector A, we all know that the dot product of the 0 vector with anything is 0 all the time, and that's why 0 vector satisfies this condition, and that's why 0 vector is a member of my set. The first criterion is checked. Let's check the second criterion. Second criterion, if you remember from the previous slide, is closedness under addition. Here's my check. I start off with 2 elements of my set. I interpret what that means. That means that each of them individually perpendicular to my fixed A vector. That's exactly what it means. This is the interpretation of the condition of being in this set. Here's the condition. Now, I'd like to test a similar condition for the sum. Here's the test for the sum. I test the sum of xy with A. And here the place where we're going to use the properties of the dot product. We know that the dot product is subject to distributive law. So we can distribute the vector A across the terms. Here's my distribution. Individually, each term here, this term 0 and this term 0, it comes from here. And we conclude that the left-hand side here is 0. So the vector in the brackets is subject to this condition. And so we finally conclude that the vector in the brackets is a member of my set. Second criterion is checked. Each individual step is very easy. I mean, and that's why the proof in general is easy. But this ability to construct present a structural coherent argument, it's the skill we're trying to build in you. And you can only build this skill by just watching and then repeating this with some other examples. The third criterion, if you remember, that's closedness under multiplication. This time we look at the field of scale as real numbers. So I start off with these 2 objects. Lambda is a scalar. X is an element in my set. I do the interpretation, what that means. That's exactly what it means. My vector x is subject to this condition. Now, because I want to test my scaled vector against this condition, here's my test. Here's the scale vector. Dot product with the A. We all know that the dot product is subject to what we call the associative law, meaning that I can put the brackets here in a different order. Here's my brackets in a different order. The number in these brackets now is 0 because of this, and the whole thing becomes 0. And that is the conclusion, that my scaled vector is an element of my set. You see, for 2 criteria here, for this one and for this one, the actual argument was given here. It was given by the distributive law of the scalar products. Here it was given by the associative law of the of the dot products. I said scalar, I meant dot products. Distributive law of the dot products, and another associative law of the dot product. There is something in every argument, there is something which does the job for you. And you have to be able to identify this something. Actually, that's the argument in relation to S1. S2, question 16, it says, show that this is not a subspace. This is easy. If you want to show something is not a subspace, again, you use this subspace theorem, but this time you just present a counterexample which fails one of the criteria. And for S2, the example is easy. If you just, obviously, vector 0 doesn't belong to this S2 because vector 0 doesn't make this condition satisfied. And that's why this first criterion is failed for S2, and that's why S2 is not a subspace. These examples, the examples of this type, the examples of subspaces of this type, later on in your later mathematical study, you will learn they're called the orthogonal complement subspaces. And it's just a term, doesn't really mean much at this stage. But later on, sometimes I will refer to this. I will refer to this lemma if I need to reference it. I will call it the orthogonal complement subspaces lemma. So it's a lemma which shows that the subspace or set of this structure, which is called the orthogonal complement, is a subspace.